Reflection and refraction. Describe what happens when a wave reaches a boundary between two media. Describe the law of refraction. Describe the type of images that are produced by plane mirrors. Describe what happens when light is incident on a rough surface. Describe what happens to sound energy that is not reflected. Describe what happens when a wave that is traveling at an angle changes its speed upon crossing a boundary between two media. Describe what causes sound waves to refract. Describe what causes the refraction of light. Describe what causes the appearance of a mirage. Describe what causes the dispersion of light. Describe the conditions necessary for seeing a rainbow. Describe what causes total internal reflection to occur. Let's look at the big idea. When waves interact with matter, they can be reflected, transmitted, or a combination of both. Waves that are transmitted can be refracted. When you shine a beam of light on a mirror, the light doesn't travel through the mirror, but is returned by the mirror's surface back into the air. When sound waves strike a canyon wall, they bounce back to you as an echo. When a wave transmitted along a spring reaches a wall, it reverses direction. In all these situations, waves remain in one medium rather than enter a new medium. These waves are reflected. In other situations, such as when light passes from air into a transparent medium like water, waves travel from one medium into the other. When waves strike the surface of a medium at an angle, their direction changes as they enter the second medium. These waves are refracted. This is evident when a pencil in a glass of water appears to be bent. Usually waves are partly reflected and partly refracted when they fall on a transparent medium. When light shines on water, for example, some of the light is reflected and some is refracted. To understand this, let's see how reflection occurs. How can you make an object invisible? Obtain two small heat-resistant beakers, one smaller than the other. Place the smaller beaker inside the larger beaker. Pour light vegetable oil or baby oil into both beakers until the smaller beaker is completely submerged. Observing. What did you observe when the oil filled both beakers? Predicting. Do you think you would observe the same results if the beakers were filled with other clear liquids? Making generalizations. What makes an object visible? Reflection. When a wave reaches a boundary between two media, usually some or all of the wave bounces back into the first medium. The return of a wave back into its original medium is called reflection. Suppose you fasten a spring to a wall and send a pulse along the spring length, as illustrated in 29.1. The wall is a very rigid medium compared to the spring. As a result, all the wave energy is reflected back along the spring rather than transmitted into the wall. Waves that travel along the spring are almost totally reflected at the wall. Figure 29.1. A wave is totally reflected when it reaches a completely rigid boundary. If the wall is replaced with a less rigid medium, such as the heavy spring shown in figure 29.2, some energy is transmitted into the new medium. Some of the wave energy is still reflected. The incoming wave is partially reflected. A metal surface is rigid to light waves that shine upon it. Light energy does not propagate into the metal, but instead is returned in a reflected wave. The wave reflected from a metal surface has almost the full intensity of the incoming wave, apart from a small energy losses due to the friction of the vibrating electrons in the surface. This is why metals such as silver and aluminum are so shiny. They reflect almost all the frequencies of visible light. Other materials such as glass and water are not as rigid to light waves. 29.2. When the wave reaches the heavy spring, it is partially reflected and partially transmitted. If you look at your blue shirt in a mirror, what is the color of its image? What does this tell you about the frequency of light incident upon a mirror compared with the frequency of light after it is reflected? The color of the image will be the same as the color of the object because the frequency of light is not changed by reflection. When light shines perpendicularly on the surface of still water, about 2% of its energy is reflected and the rest is transmitted. When light strikes glass perpendicularly, about 4% of its energy is reflected, except for slight losses, the rest is transmitted. Concept check. What happens when a wave reaches a boundary between two media? 29.2. The law of reflection. In one dimension, reflected waves travel back in the direction from which they came. Let a ball drop to the floor and it bounces straight up along its initial path. In two dimensions, the situation is a little different. A pool ball hitting the side of a pool table at an angle bounces back at the same angle in a new direction. Likewise with light. The direction of incident and reflected waves is best described by straight line rays. Incident rays and reflected rays make equal angles with a line perpendicular to the surface called the normal, as shown in figure 29.3. Figure 29.3. In reflection, the angle between the incident ray and the normal is equal to the angle between the reflected ray and the normal. The angle between the incident ray and the normal, called the angle of incidence, is equal to the angle between the reflected ray and the normal, called the angle of reflection. Angle of incidence equals angle of reflection. The law of reflection describes the relationship between the angle of incidence and the angle of reflection. The law of reflection states that the angle of incidence and the angle of reflection are equal to each other. The incident ray, the normal, and reflected ray all lie in the same plane. The law of reflection applies to both partially reflected and totally reflected waves. Concept check. What is the law of reflection? 29.3. Mirrors. Consider a candle flame placed in front of a plain, flat mirror. Rays of light leaving the candle are reflected from the mirror surface in all directions. The number of rays is infinite, and every one obeys the law of reflection. Figure 29.4 shows only two rays that originate at the tip of the candle flame and reflected from the mirror to your eye. Note that the rays diverge, spread apart from the tip of the flame and continue diverging from the mirror upon reflection. These divergent rays appear to originate from the point located behind the mirror. Your experience is that light travels in straight lines. Therefore, you perceive the candle flame to be located behind the mirror. 29.4. The virtual image is formed behind the plane mirror and is located at a position where the extended reflected rays, broken lines, converge. Virtual image is an image that appears to be in a location where light does not really reach. Plane mirrors produce only virtual images. Your eye cannot ordinarily tell the difference between an object and its virtual image because the light that enters your eye is entering in exactly the same manner as it would without the mirror if there really were an object where you see the image. Notice that the image is as far behind the mirror as the object is in front of the mirror, and the image and object are the same size. Where is your mirror image? 1. Look at your face in a mirror. 2. Now look at something on the surface of the mirror, such as a dust speck. 3. Do you have to adjust your eyes to refocus from looking at your image to looking at the dust on the mirror surface? 4. Think. Is your image farther away than the mirror surface? As illustrated in figure 29.5, when you view yourself in a mirror, your image is the same size your identical twin would appear if located as far behind the mirror as you are in front, as long as the mirror is flat. Note in figure 29.6a that the woman and her image have the same color of clothing, evidence that the light doesn't change frequency upon reflection. Interestingly, her left-right axis is no more reversed than her up-down axis. The axis that is reversed, as shown in figure 29.6b, is front to back. That's why it seems her left hand faces the right hand of her image. The law of reflection still holds for curved mirrors as illustrated in figure 29.7. However, when the mirror is curved, the sizes and distances of objects and images are no longer equal. 29.5. For reflection in a plane mirror, object size equals image size and object distance equals image distance. 29.6. A. The image is as far behind the mirror as she is in front. B. Her front-back axis is the only axis that is reversed. 29.7. The law of reflection holds for curved mirrors. A. The image formed by a convex mirror is smaller than the object. B. When the object is close to a concave mirror, the image can be larger than the object. The virtual image formed by a convex mirror, a mirror that curves outward, is smaller and closer to the mirror than the object is. When the object is closer to a concave mirror, a mirror that curves inward like a cave, the virtual image can be larger and more distant than the object. Concept check. What kind of images do mirrors produce? 29.4. Diffuse reflection. When light is incident on a rough surface, it is reflected in many directions. Diffuse reflection, as shown in figure 29.8, is the reflection of light from a rough surface. Although each ray obeys the law of reflection, the many different angles that incident light rays encounter at the surface cause reflection in many directions. What constitutes a rough surface for some rays may be a polished surface for others. If the differences in elevations in a surface are small, less than about 1/8, the wavelength of the light that falls on it, the surface is considered polished. Figure 29.8. Diffuse reflection occurs when light is reflected on a rough surface. A surface may be polished for long wavelengths, but not polished for short wavelengths. Whether a surface is a diffuse reflector or a polished reflector depends on the wavelength of the waves it reflects. Light that reflects from this page is diffuse. The page may be smooth to a long radio wave, but to a short wavelength of visible light, it is rough. Rays and light incident on this page encounter millions of tiny flat surfaces facing in all directions. So they are reflected in all directions, as illustrated in figure 29.9. A microscopic view of an ordinary piece of paper shown in figure 29.10. Diffuse reflection allows us to read the page from any direction or position. We see most of the things around us by diffuse reflection. Concept check. What happens when light is incident on a rough surface? Figure 29.9. Diffuse reflection allows us to see most things around us. A. Light is diffusely reflected from paper in many directions. B. Light incident on a smooth mirror is only reflected in one direction. Figure 29.10. Ordinary paper like this textbook page has a rough surface that can be viewed with a microscope. 29.5. Reflection of sound. An echo is reflected sound. The fraction of sound energy reflected from a surface is more when the surface is rigid and smooth, and less when the surface is soft and irregular. Sound energy that is not reflected is absorbed or transmitted. Sound reflects from all surfaces: the walls, ceiling, floor, furniture, and people of a room. People who design the interiors of buildings, whether office buildings, factories, or auditoriums, need to understand the reflective properties of surfaces. The study of sound is called acoustics. When the walls of a room, auditorium, or concert hall are too reflective, the sound becomes garbled. This is due to multiple reflections of sound waves called reverberations. But when the reflective surfaces are more absorbent, the sound level is lower, and the hall sounds dull and lifeless. Reflection of sound in a room makes it sound lively and full, as you have probably found out while singing in the shower. In the design of an auditorium or concert hall, a balance between reverberation and absorption is desired. The walls of concert halls are often designed with grooves so that the sound waves are diffused. This is illustrated in figure 2911a. In this way, a person in the audience receives a small amount of reflected sound from many parts of the wall, rather than a large amount of sound from one part of the wall. Figure 2911. The walls of a concert hall are carefully designed. A. With grooved walls, sound reflects from many small sections of the wall to a listener. B. With flat walls, and intense reflected sound comes from only one part of the wall. Highly reflective surfaces are often placed behind and above the stage to direct sound out to an audience. The large, shiny plastic plates in figure 2912 also reflect light. A listener can look up at these reflectors and see the reflected image of the members of an orchestra. The plastic reflectors are somewhat curved, which increases the field of view. Both sound and light obey the same rules of reflection, so if a reflector is oriented so that you can see a particular musical instrument, rest assured that you will hear it also. Sound from the instrument will follow the line of sight to the reflector and then to you. Concept check. What happens to sound energy that is not reflected? 2912, the shiny plates above the orchestra in Davies Symphony Hall in San Francisco reflect both light and sound. 29.6, refraction. Suppose you take a rear axle with its wheels attached off a old toy car and let it roll a pavement that slopes gently downward and onto a downward sloping mowed lawn. It rolls more slowly on the lawn because of the interaction of the wheels with the blades of grass. If you roll it at an angle, as shown in figure 2913, it will be deflected from its straight line course. The direction of the axle and rolling wheels is shown in the illustration. Note that the wheel that first meets the lawn slows down first because it interacts with the grass while the opposite wheel is still rolling on the pavement. Figure 2913, the direction of the rolling wheels changes when one wheel slows down before the other one. The axle pivots and the path bends towards the normal, the thin dashed line perpendicular to the grass pavement boundary. The axle then continues across the lawn in a straight line at reduced speed. When a wave that is traveling at an angle changes its speed upon crossing a boundary between two media, it bends. Water waves bend or refract when one part of each wave is made to travel slower or faster than another part. Refraction is the bending of a wave as it crosses the boundary between two media at an angle. Water waves travel faster in deep water than in shallow water. Figure 2914a shows a view from above of a straight wave crest, the bright lines, moving towards the right edge of the photo. They are moving from deep water across a diagonal boundary into shallow water. At the boundary, the wave speed and direction of travel are abruptly altered. Since the wave moves more slowly in shallow water, the crests are closer together. If you look carefully, you'll see some reflection from the boundary. In drawing a diagram of a wave, it is convenient to draw lines called wave fronts that represent the positions of different crests. At each point along a wave front, the wave is moving perpendicular to the wave front. The direction of the motion of the wave can thus be represented by rays that are perpendicular to the wave front. 2914. Water waves travel faster in deep water than in shallow water. A. The wave reflects at the boundary where the depth changes. B. The simple ray is perpendicular to the wave front it intersects. The ray in figure 2914b shows how the water wave changes direction after it crosses the boundary between deep and shallow water. Sometimes we analyze waves in terms of wave fronts, and at other times in terms of rays. Both are useful models for understanding wave behavior. Notes: although wave speed and wavelength change when undergoing refraction, frequency remains unchanged. Concept check. What causes a wave to bend? 29.7, refraction of sound. Sound waves are refracted when parts of the wave front travel at different speeds. This happens in uneven winds or when sound is traveling through air of uneven temperature. On a warm day, the air near the ground may be appreciably warmer than the air above. Since sound travels faster in warmer air, the speed of sound near the ground is increased. The refraction is not abrupt but gradual. As shown in figure 2915, Sound waves, therefore, tend to bend away from warm ground, making it appear that the sound does not carry well. Figure 2915, the wave fronts of sound are bent in air of uneven temperature. Suppose you are downwind from a factory whistle, in which case will the whistle sound louder if the wind speed near the ground is more than the wind speed several meters above the ground, or if it is less. You'll hear the whistle better if the wind speed near the ground is less than the wind speed higher up. For this condition, the sound will be refracted toward the ground. On a cold day or at night, when the layer of air near the ground is colder than the air above, the speed of sound near the ground is reduced, as illustrated in figure 2916. The higher speed of wave fronts above cause a bending of the sound toward Earth. When this happens, sound can be heard over considerably longer distances. Concept check. What causes sound waves to refract? Figure 2916. At night, when the air is cooler over the surface of a lake, sound is refracted towards the ground and carries unusually well. 29.8. Refraction of light. Ponds or swimming pools appear shallower than they actually are. A pencil in a glass of water appears bent. The air above the hot stove seems to shimmer and stars twinkle. These effects are due to the refraction of light. Changes in speed of light as it passes from one medium to another, or variations in the temperature and densities of the same medium, cause refraction. The directions of the light rays change because of refraction. Figure 2917 shows rays and wave fronts of light refracted as they pass from air into water. 2917, as a light wave passes from air into water, its speed decreases. The wave fronts would be curved if the source of light were close, just as the wave fronts of water waves near a stone thrown into water are curved. Notes: a light ray is always at right angles to the wave front. If we assume that the source of light is the sun, then it is so far away that the wave fronts are practically straight lines. Note that the left portion of the wave fronts are the first to slow down when they enter the water, or right portions if you look along the direction of travel. The refracted ray of light, which is at right angles to the refracted wave fronts, is closer to the normal than is the incident ray. Compare the refraction in the case to the bending of the axle's wheel in figure 2913. When light rays enter a medium in which their speed decreases, as when passing from air into water, the rays bend towards the normal. But when light rays enter a medium in which their speed increases, as when passing from water into air, the rays bend away from the normal. Figures 2918 shows a laser beam entering a container of water at the left and exiting at the right. The path would be the same if the light entered from the right and exited at the left. The light paths are reversible for both reflection and refraction. If you can see somebody by way of a reflective or refractive device, such as a mirror or a prism, then that person can see you or your eyes by looking through the device also. 2913, the direction of the rolling wheels change when one wheel slows down before the other one. The laser beam bends towards the normal when it enters the water and away from the normal when it leaves. As figure 2919a shows, a thick pane of glass appears to be only 2/3 its real thickness when viewed straight on. For clarity, the diameter of the eye pupil is made larger than true scale. Similarly, water in a pond or pool appears to be only 3/4 its true depth. In figure 2919b, the fish in the water appear to be nearer to the surface than it really is. It also seems closer. Another illusion is shown in figure 2919c. Light from the root beer is refracted through the sides of the thick glass, making the glass appear thinner than it is. The eye, accustomed to perceiving light traveling through straight lines, perceives the root beer to be at the edge of the glass along the broken lines. These effects are due to the refraction of light whenever it crosses a boundary between air and another transparent medium. Concept check. What causes the refraction of light? 2919. There are many effects of refraction. A. The apparent depth of a glass block is less than the real depth. B. The fish appears to be nearer than it actually is. C. The full glass mug appears to hold more root beer than it actually does. 29.9. Atmospheric refraction. Although the speed of light in air is 0.03% less than its speed in a vacuum, in some situations atmospheric refraction is quite noticeable. One interesting example is the appearance of a distorted image called a mirage. A mirage is caused by the refraction of light in Earth's atmosphere. On hot days, there may be a layer of very hot air in contact with the ground. Since molecules in hot air are farther apart, light travels faster through it than through the cooler air above. The speeding up of the part of the wave nearest the ground produces a gradual bending of the light rays. If the speed of light were the same for various temperatures and densities of air, would there still be mirages? No. There would be no refraction if light traveled at the same speed in air at different temperatures and densities. This can produce an image, say, of a palm tree as in figure 2920. The image appears upside down to an observer at the right, just as if it were reflected from the surface of water. But the light is not reflected, it is refracted. Wave fronts of light are shown in figure 2921. The refraction of light in air, in this case, is very much like the refraction of sound in figure 2915. Undeflected wave fronts would travel at one speed and in the direction shown by the broken lines. Their greater speed near the ground, however, causes the light ray to bend upward as shown. A motorist experiences a similar situation when driving along a hot road that appears to be wet ahead. The sky appears to be reflected from the wet surface, but in fact, light from the sky is being refracted through a layer of hot air. 2920. The refraction of light in air produces a mirage. Wave fronts of light travel faster in the hot air near the ground, thereby bending the rays of light upward. A mirage is not, as some people mistakenly believe, a trick of the mind. As figure 2922 illustrates, a mirage is formed by real light and can be photographed. When you watch the sunset, you see the sun for several minutes after it has really sunk below the horizon. This is because light is refracted by Earth's atmosphere as shown in figure 2923. Since the density of the atmosphere changes gradually, the refracted rays bend gradually to produce a curved path. The same thing occurs at sunrise, so our daytimes are about 5 minutes longer because of atmospheric refraction. 2922. A driver might see a mirage on a hot day. The wet street is actually dry. 2923. When the sun is already below the horizon, you can still see it. When the sun or moon is near the horizon, the rays from the lower edge are bent more than the rays from the upper edge. This produces a shortening of the vertical diameter and makes the sun or moon look elliptical instead of round, as in figure 2924. Concept check. What causes the appearance of a mirage? 2924. Atmospheric refraction produces a pumpkin sun. 2910. Dispersion in a prism. Chapter 27 discussed how the average speed of light is less than c in a transparent medium. How much less depends on the medium and the frequency of the light. Light of frequencies closer to the natural frequency of the electron oscillators in a medium travels more slowly in the medium. This is because there are more interactions with the medium in the process of absorption and re-emission. Since the natural or resonant frequency of most transparent mediums is in the ultraviolet part of the spectrum, visible light of higher frequencies travels more slowly than light of lower frequencies. Violet light travels about 1% slower in ordinary glass than red light. Why do stars twinkle? Look across a hot stove or hot pavement. Describe what you observe. What is a possible explanation for what you are seeing? The next time you are outside in a clear night, try to notice the twinkling of stars in the nighttime sky. What causes this twinkling? Think. Why are many observatories located atop mountains? Light waves of colors between red and violet travel at their own intermediate speeds. Since different frequencies of light travel at different speeds in transparent materials, they will refract differently and bend at different angles. When light is bent twice at non-parallel boundaries, as in a prism, the separation of the different colors of light is quite apparent. This separation of light into colors arranged according to their frequency, as illustrated in 2925, is called dispersion. 2925. Dispersion through a prism occurs because different frequencies of light travel at different speeds. 2911. The rainbow. A spectacular illustration of dispersion is the rainbow. In order for you to see a rainbow, the sun must be shining in one part of the sky, and the water droplets in a cloud or in falling rain must be in the opposite part of the sky. When you turn your back to the sun, you see the spectrum of colors in a rainbow, as illustrated in figure 2926. All rainbows would be completely round if the ground were not in the way. 2926. The rainbow is seen in a part of the sky opposite the sun and is centered on the imaginary line extending from the sun to the observer. Dispersion by a raindrop. Consider an individual spherical raindrop as shown in figure 2927. Follow the ray of sunlight as it enters the drop near the top surface. Some of the light here is reflected, not shown, and the rest is refracted into the drop. At this first refraction, the light is dispersed into its spectral colors. Violet is bent the most and red the least. The rays reach the opposite part of the drop to be partly refracted out into the air, not shown, and partly reflected back into the water. Part of the rays that arrive at the lower surface of the drop are refracted into the air. Figure 2927, dispersion of sunlight by a water drop produces a rainbow. This second refraction is similar to that of a prism, where refraction at the second surface increases the dispersion already produced at the first surface. This twice refracted, once reflected light is concentrated in a narrow range of angles, observing a rainbow. Each drop disperses a full spectrum of colors. An observer, however, is in a position to see only a single color from any one drop, as illustrated in figure 2928. If violet light from a single drop enters your eye, red light from the same drop falls below your eye. To see red light, you have to look at a drop higher in the sky. You'll see the color red when the angle between a beam of sunlight and the dispersed light is 42 degrees. Figure 2928, sunlight strikes two sample drops and emerges as dispersed light. The color violet is seen when the angle between the sunbeam and dispersed light is 40 degrees. You don't need to look only upward at 42 degrees to see dispersed red light. You can see red by looking sideways at the same angle or anywhere along a circular arc swept out at 42-degree angle. The dispersed light of other colors is along similar arcs, each at their own slightly different angle. Altogether, the arcs for each color form the familiar rainbow shape. If you rotate the triangle shown in figure 2929, you sweep out the portion of the cone with your eye at the apex. The rainbow that disperses light to you lie at the far edges of such a cone. The thicker the region of water drops, the thicker the conical edge you look through, and the more vivid the rainbow. Figure 2929, only rainbows along the dashed arc disperse red light to the observer at a 42-degree angle. Your cone of vision that intersects the raindrops creating your rainbow is different from that of a person next to you. So when your friend says, "Look at the beautiful rainbow," you can reply, "Okay, move aside so I can see it too." Everybody sees his or her own personal rainbow. So when you move, your rainbow moves with you. This means you can never approach the side of a rainbow or see it end on, as in the exaggerated view of figure 2926. You can't get to the end, hence the expression, looking for the pot of gold at the end of the rainbow, means pursuing something you can never reach. Often, a larger secondary bow with colors reversed can be seen arching at a greater angle around the primary bow. Figure 2930. Light from droplets inside the rainbow form a bright disk with the colored rainbow at its edge. The sky appears darker outside the rainbow because there is no light exiting raindrops in the way that produces the main rainbow. Notice the dimmer secondary bow. You can see the secondary bow in figure 2930. The secondary bow is formed by similar circumstances and is a result of double reflection within the raindrops, as illustrated in figure 2931, because most of the light is refracted out the back of the water drop during the extra reflection. The secondary bow is much dimmer. Figure 2931. Double reflection in a water drop produces a secondary bow that is much dimmer than the primary bow. Think, if light travels at the same speed in raindrops as it does in air, would we still have rainbows? No. If there is no change in speed, there is no refraction. If there is no refraction, there is no dispersion of light, and hence no rainbow. Point to a wall with your arm extended to approximate a 42-degree angle to the normal of the wall. Rotate your arm in a full circle while keeping the same 42-degree angle. What shape does your arm describe? What shape on the wall does your fingers sweep out? Your arm describes a cone, and your finger sweeps out a circle. Likewise with rainbows. 2912. Total internal reflection. Vision in 3 dimensions depends on the fact that both eyes give impressions simultaneously, or nearly so, each eye viewing a scene from a slightly different angle. To convince yourself of this, hold an upright finger at arm's length and see how it switches position relative to the background as you alternately close each eye. The view seen by each eye is different. The combination of views in the eye-brain system gives depth. Look at figure 2718. A pair of photographs or movie frames taken a short distance apart, about average eye spacing, can be seen in 3D when the left eye sees only the left view and the right sees only the right view. Slideshows or movies accomplish this by projecting the pair of views through polarization filters onto a screen. The critical angle. At a certain angle, called the critical angle, you'll notice that the beam no longer emerges into the air above the surface. The critical angle is the angle of incidence that results in the light being refracted at an angle of 90 degrees with respect to the normal. As a result, the intensity of the emerging beam reduces to 0. When the flashlight is tipped beyond the critical angle, 48 degrees from the normal in water, the beam cannot enter the air. It is only reflected. The beam is experiencing total internal reflection, which is the complete reflection of light back into its original medium. Total internal reflection occurs when the angle of incidence is larger than the critical angle. The only light emerging from the water surface is that which is diffusely reflected from the bottom of the bathtub. This procedure is shown in figure 2932. The proportions of light refracted and reflected are indicated by the relative lengths of the solid arrows. The light reflected beneath the surface obeys the laws of reflection. The angle of incidence is equal to the angle of reflection. The critical angle for glass is about 43 degrees, depending on the type of glass. This means that within the glass, rays of light that are more than 43 degrees from the normal to the surface will be totally internally reflected at the surface. You can observe total internal reflection in your bathtub. A through D, light emitted in the water at angles below the critical angle is partly refracted and greatly reflected at the surface. E, at the critical angle, the emerging beam skims the surface. F, past the critical angle, there is total internal reflection. Rays of light in the glass prism shown in figure 2933, for example, meet the black surface at 45 degrees and are totally internally reflected. They will stay inside the glass until they meet a surface at an angle between 0, straight on, and 43 degrees to the normal. Total internal reflection is as the name implies. Total, 100%. Silverized or aluminized mirrors reflect about 90 to 95% of incident light and are marred by dust and dirt. Prisms are more efficient. This is the main reason prisms are used instead of mirrors in many optical instruments. Figure 2933 illustrates how prisms can be used to reflect light. 2933 prisms are more efficient at reflecting light than mirrors because of total internal reflection. Total internal reflection in diamonds. The critical angle for diamonds is 24.6 degrees, smaller than in any common substance. This small critical angle means that light inside a diamond is more likely to be totally internally reflected than to escape. All light rays more than 24.6 degrees from the normal to the surface in a diamond are kept inside by total internal reflection. As shown in figure 2934, when a diamond is cut as a gemstone, light that enters at one facet is usually totally internally reflected several times without any loss in intensity before exiting from another facet in another direction. A small critical angle plus the pronounced refraction because of the unusually low speed of light in diamond produces wide dispersion and a wide array of brilliant colors. Figure 2934, the brilliance of diamonds is a result of total internal reflection. Optical fibers. Optical fibers, sometimes called light pipes, are transparent fibers that pipe light from one place to another, as illustrated in figure 2935. They do this by a series of total internal reflections. Optical fibers are useful for getting light to inaccessible places. Mechanics and machinists use them to look at the interiors of engines, and physicians use them to look inside a patient's body. Light that shines down some of the fibers illuminates the scene and is reflected back along others. Optical fibers are important in communications and have been replacing bulky and expensive copper cables to carry telephone messages between major switching centers. 2935. In an optical fiber, light is piped from one end to the other by a succession of total internal reflections. More information can be carried in the high frequencies of visible light than in the lower frequencies of electric current. Notes: light travels slowly in a diamond, but even more slowly in a silicon carbide crystal called carborundum. Concept check. What causes total internal reflection to occur? Summary. When a wave reaches a boundary between two media, usually some or all of the wave bounces back into the first medium. The law of reflection states that the angle of incident and the angle of reflection are equal to each other. Plane mirrors produce only virtual images. When light is incident on a rough surface, it is reflected in many directions. Sound energy that is not reflected is absorbed or transmitted. When a wave that is traveling at an angle changes its speed upon crossing a boundary between two media, it bends. Sound waves are refracted when parts of a wave front travel at different speeds. Changes in the speed of light as it passes from one medium to another, or variations in the temperature and densities of the same medium, cause refraction. A mirage is caused by the refraction of light in Earth's atmosphere. Since different frequencies of light travel at different speeds in transparent materials, they will refract differently. In order for you to see a rainbow, the sun must be shining in one part of the sky and water droplets must be in the other part of the sky. Total internal reflection occurs when the angle of incidence is larger than the critical angle.